the capacitance of a parallel plate capacitor in air between them. So what was the capacitance, Aisha? Do you remember? Yeah, what was the capacitance when nothing was in here? So what was the capacitance?
Q by V.
So A E epsilon, yeah, Q by V, that is correct, but we ultimately got the result. So this is the general, yeah, so A E epsilon naught by D, correct. So this was the capacitance that we got. Now in the second part, we filled this capacitor with some dielectric constant K. So then what was the capacitance that we got?
E epsilon naught K by D.
Absolutely right. So this was what we got. And then we partially filled. So after this, we partially filled this capacitor with some dielectric constant and thickness T. So then what was the capacitance? Do you remember? Yes. The total distance was A E epsilon naught would be there. Now what was there in the denominator? Am I audible clearly?
So your voice is breaking.
Yes, Aisha, am I audible?
Yes.
Can you hear me? Yeah. So what was the capacitance for the partially filled dielectric parallel plate capacitor? What was the capacitance?
D minus D plus D by K.
Yeah. So this was the capacitance. Good, good. So you remember. And then I partially filled it with some conductor. So this was this conductor. This is some conductor of, right. Then what was the capacitance then? Yeah, what was the capacitance then? This was AE epsilon naught by D minus T, because the K value or dielectric constant for a conductor or a metal is infinity. So this was zero, then we got this. Right, so this was what we got for the parallel plate capacitor, right, Aisha?
Yes.
Now we'll calculate now we'll calculate the capacitance of a, so now we'll calculate the capacitance of a spherical plate capacitor. Okay, so what is the design of a spherical plate capacitor? We have two hollow spheres, right? So this is charge Q and radius R1. And then we have this outer hollow sphere. So this is ground. Okay. And if it is grounded, so it provides a negative charge, right? This we have done. Do you remember?
Yes.
So it will provide a minus Q charge to this sphere. So we have this. So then we have this radius which is R. Okay. Clear up to this point?
Yes, sir.
So we have to calculate the capacitance. As you say, this is Q by V, right? This is the capacitance. So we have to calculate the potential difference between this sphere and this sphere. Let's say this is V1 and then this is V2. So we have to calculate the potential which is V1 minus V2. Is this clear, Aisha?
Yes.
Okay, so now you'll have to remember what we did for the hollow sphere. So let me ask you this. That we have a hollow sphere and the charges are here, right? And we have this point. So we had three regions for the hollow sphere. One was inside, the other was surface, and then we have this outer side, outside. So this has some radius r. So what was the potential inside, Aisha? Do you remember?
KQ by capital R.
KQ by capital R, which was radius. Absolutely right. Good. So which means you remember. And what was the V surface?
KQ by capital R.
KQ by capital R, which means radius again. So KQ by capital R. And what was V outside?
KQ by small r.
KQ by whatever was the distance, which was smaller. Good. So you remember. Now we can do this question easy. So at this point, how many contribution would be there? Let us calculate V1 first. So how many contribution would be there for this point? How many contribution would be there? Yes, two, right? Because we have this sphere, this one sphere, and then we have this second sphere. So V1 would be V of, and this is surface, surface of small sphere. And what about the second bigger sphere? What is this point? What is this point for the bigger sphere? Inside, right?
Yes, sir.
So inside, and then this one is larger, right? Okay. So now can you tell me what would be V surface for the smaller one? Yes. What is V surface for the smaller sphere?
KQ by capital R.
KQ by what is
R2.
capital R? R
R.
R1, right? R1 is the radius, right?
Yes.
Okay, and now tell me about this larger sphere. What would be the potential?
KQ by R2.
What is the charge here? Minus Q, right?
Yes.
So good. This would be the answer. So we have KQ by R1 Okay. So then what is the potential we have? V1 is KQ by R1 minus KQ by R2. Okay. Now we have to calculate what is V2. So for V2, what is this smaller sphere? What is uh, what is the position of this? What is the position of this point for the smaller sphere? Yes, this point, what is
Outside.
outside, right? So this is the outside. And then this bigger sphere. So for the bigger sphere, what is this point?
Surface.
Surface, right? Good. So we have this surface and this is large. Okay, so what is this V outside? Yes. What is,
KQ by R1.
yeah, R1. So outside is distance,
R2.
R2, right? This is R2. Plus, what is this surface one?
PQ by R2.
Minus, right? We have minus and R2. Good. So this is KQ by R2 minus KQ by R2. So this is 0. And you already know that when we earth something, so when we apply earthing, so what is the potential of that surface when we apply the earthing? Yeah, when we apply the earthing, what was the potential of the surface? It becomes 0, right? It
Yes,
becomes 0.
your
That
voice
is
is
what.
breaking.
Yes. Yes. What did you say?
Your voice was breaking.
Oh, my voice was breaking. So am I? I was saying that. I was saying that when I earth this surface. So due to applying the earthing, the potential at this surface becomes 0. This we have learned, right? Right, Aisha?
Yes.
Yeah. So this is what we have proven. So let us go back to the. So this is capacitance. Let us go back to potential energy. This was what potential, right? So when we were calculating the potential, oh, this one when we were calculating the potential, right? Yes, maybe in here we have. Yeah. So we were applying the earth, right? When we applied the earthing, then potential becomes what? Right? Potential becomes 0.
Zero.
So this is what we have proven in here, right? This is what we got. The potential is 0. Okay, now what would be the potential difference on this surface? So this we have already calculated. This is V1 minus V2. So V1 is KQ by R1 minus of KQ by R and minus of V2, which is 0. So we have KQ by R1 minus KQ by R. Okay, this is the potential that we have. Now we have to calculate the capacitance, right? So to calculate the capacitance, we know that this is how much? This is Q by V. So then Q is how much? This is V, which is KQ by R1 minus KQ by R. So this is Q by, and we take KQ outside. So this is 1 by R1 minus 1 by R. So Q cancels, and K is what? 1 by 4 pi epsilon naught. So 1 by 4 pi epsilon naught. And this is R1 into R2 and R2 minus R1, and this goes over the top. So this is 4 pi epsilon naught R1 R2 divided by R2 minus R. Right. So this is the capacitance of a spherical plate capacitor. Is this clear to you, Aisha?
Yes, sir.
Okay, so please note it down from here. Right, please note it down. And whenever you want me to scroll down the screen, you guys, you tell. Yeah, whenever you need me to scroll down the screen, you please tell.
Done, sir.
Okay, so please note it down.
Done, sir.
Done. So okay, whenever you have completed, please let me
Done, sir.
know. Okay, so this was about the spherical plate capacitor. Now we have a cylindrical capacitor. Right. So we have what is the geometrical design? So we have this cylinder, right? This is the inside one, and then we have this outside. Right? And the length of this cylinder is L. The inner radius is R, and the outer radius is this is R1, this is R2, and this is again Earth, right? So this has minus Q charge and this has plus Q charge. Okay. So this is the construction of a cylindrical capacitor. So how do we calculate the so to calculate the capacitance we have to calculate the voltage, right? So how do we calculate the potential difference between this point and this point? So we have to calculate V1 minus V2 as we did in the previous case. So what do we know about the cylindrical capacitor or the cylindrical thing, hollow cylinder? So for hollow cylinder, the electric field is lambda by 2 pi epsilon naught r. This is we know. So can you tell me that what is the relation between potential difference and electric field? So we did this part extensively. Can you recall?
dV by dr.
Yeah, so that is E is minus dV by dr. This is the electric field as gradient of potential. This we know. But I am asking the opposite thing. The opposite thing. How V is related with. So you have told me E related with. I am asking how V related to E.
Um, E dot dr.
Yes, 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 you are right. Final minus V initial is what? So minus E dot dr, right? And initial to final. This is the change in potential, right?
Yes, sir.
Do you remember? Okay, good. So because we can prove it from here also. We know that work done in bringing a charge from initial point to final point is what? Minus Q E dot dr and initial to final point. And we also know that work done in bringing a charge from initial to final point is Q V final minus initial. So this cancels and V final minus V initial is minus of initial to final E dot. Right, Aisha?
Yes,
Okay, so remembering this, right? Remembering this, we have the electric field, right? We have this electric field and we want to calculate V1 minus V2, right? So remember your final point is 1. So minus of this is, this would be 1 and this would be 2. Is this clear?
yes, sir.
So E dot dr and their angle is 0. So this is E dr. Okay, so this is minus of R2 R1 and E is lambda by 2 pi epsilon naught R dr. So this will become lambda by 2 pi epsilon naught is common and we have this integral R2 to R1 and 1 by R dr. So what is the integral of 1 by x dx? Do you remember? What is the integral of 1 by x, Aisha? Yes. Did you forget? Yeah.
I
Got
remember
that?
it actually.
Okay. So yeah, let me, yeah. So this is log x, right? This is the integral. Now do you remember? Yes.
Yes, sir.
Okay. So this would be how much? So it will be minus lambda by 2 pi epsilon naught and this is log of r and we have to put upper limit and lower limit. So this is minus of lambda by 2 pi epsilon naught. And first we put the upper limit. So what would be here? What would be in here if we first put the upper limit?
R1,
Yes.
R1,
Function is, no. Function is log r. Function is log x and you have to put x1 and x2. So what would be in here first? Yes. So let me tell you this way. If I have x square and I have to put 3 and 2. So first function is x square. So first in place of x, I put 3. So this would be how much? This would be how much, Aisha? Yes, this would be how much? In place of x square, I have to put 3. So what would be in here?
9.
3 square, right? This
Okay.
is the upper limit and minus of lower limit. So what would be in here? Minus of, yes,
2 square.
minus 2 square. Absolutely right. Good. So this would be, so function is x square. Now function is log r, log x. So if I put the upper limit, so what would be in here first?
R1.
No, no, no. Function is log. Log is function. So log of r,
R.
right? Minus of what?
Log of R2.
Yes. Now you are correct. So this would be the function. And do you remember what is log A minus log B? Do you remember? What is this? Do you remember the property of log? What is log A minus log B?
Favorite log 1 minus A by B.
Yes, log of A by B. Yes, good. So this is a property of log. Good. So this is minus lambda by 2 pi epsilon naught and log of R1 by R. Good. Now, what is let me remind you another property of log. Let's say you have log of x to the power 3. So how do you solve this power? Yeah. Where does this power go? Yes. Where does this power go? So this power goes in this, right, comes down and this becomes 3 log x. So do you recall this property of log?
Yes.
Yes. Do you recall this property?
Yes.
Okay. So similarly, let's say if I have log 2 log or minus 2 log x, whatever. So then if I take 2 in the inside of log, so this will become what? Log of x square. Reverse of this property. Is this clear?
Yes.
Clear. So similarly, what I do is that I take this minus inside. So inside the log. So this will go in the power, right? So log of R1, R2 and power how much? What would be the power? I took this minus inside the log. So this will go in the power. So how much would be the power?
Point.
Minus 1. Right. So let's say I have this minus 2 log of x. So if I take this minus 2 inside, so this would be log of x to the power minus 2. Similarly, this is minus 1, so it goes in the power. And if this is power minus 1, so this will reverse. So this will reverse it and it will become R2 by R. So is this point clear to you?
Yes.
So this is my potential. This is my potential, and if I solve this further, so capacitance is Q by V. So Q by V is how much? Lambda by 2 pi epsilon naught log of R2 by R1. So this 2 pi epsilon naught goes in the numerator. This becomes Q, and this is 2 pi epsilon naught. divided by lambda and R2 by R1. So can you tell me what is this linear charge density lambda? What is this linear charge density?
Q by L.
Yes,
Q by L.
Q by yes, Q
Linear
by
charge L.
L, absolutely right. So Q by L. Right, good. So this is Q by L. So if I replace this uh, Q by L, right? And then log of R2 by R. So this Q cancels and this L goes in the numerator. So this is 2 pi epsilon naught L by log R2 by R. So this is the capacitance of a cylindrical capacitor. 2 pi epsilon naught L divided by log of R2 by R. Any part which is not clear to you? Yes.
It's clear.
Okay, so please note it down, Aisha. Please note it down from here. So, yeah, note this point. And this point is not. Yes, whenever you want me to scroll down the screen, please. So, yeah, note down from here.
Also, down.
Done. Okay, so now we have calculated the capacitance of different kinds of capacitor. So first we calculated the capacitance of parallel plate capacitor, and then we calculated the capacitance of spherical capacitor. Now we calculated the capacitance of a cylindrical capacitor. So now can you tell me that if I have a cylindrical capacitor, right? This is my cylindrical capacitor. Okay, and then I have this outside. And this is ground. Right? This is minus Q. This is plus Q. Okay, now what I do is that I put a dielectric slab in between in this capacitor. So I put a dielectric slab. So can you tell me what would be the capacitance? So cylindrical capacitor when a dielectric is placed in between. So what would be the capacitance? Can you tell me? This is K. Yes. Can you guess, Aisha? Yes,
Epsilon
Aisha.
naught K.
Yeah, absolutely right. 2 pi epsilon naught K, and rest remains the same. Good one. So yeah, this would be the capacitance. Right, Aisha.
Yes.
Okay, so please note it down, and then we'll understand the next topics.
Also,
Okay, so now let's keep this here, and now what do we have? We have force between parallel plate capacitor. So let us say that we are calculating the force on right? So we have this parallel plate capacitor, and we are calculating the force on this charge. So this is minus, this is plus, so it is plus q and it is minus q. And we are calculating the force on this charge, right? So what would be the force on this charge? Yes. What would be the force on this charge?
Mm,
Yes. So force is we already know. This is Q into E, correct?
yes, sir.
So we are calculating force on minus Q charge. So this would be how much? This is minus Q, and we have to figure out what is this electric field that we have placed each charge, right? So we have to figure out what is this electric field. Okay. So what is the electric field inside this region? What is the electric field? What is the value of electric field that you have? In this region, what is the electric field? This you already know. Okay, forgotten. What is the electric field inside the plate?
I don't remember.
So this is sigma by epsilon naught, right? Correct?
Yes,
So then this is sigma is how much? Sigma is due to this, right? Due to this charge. So this is Q by A and epsilon naught. So then what would be force? Force would be minus Q and Q by A E epsilon naught. So this is how much? Minus Q square by A E epsilon. This is the force on minus Q charge due to this. Is this part clear to you?
yes, sir.
Okay, so please note it down. Oh, but one more. We have, yeah. So, what is the electric field due to this sheet? What is the electric field due to this sheet? So that is sigma by 2 epsilon naught, right?
Yes,
So this would be 2 and this would be 2 and then this would be 2. So please correct. Okay, so this is E due to Q charge. Okay, E due to Q charge. So E due to Q charge. Right, please, and if you have any doubts, so please ask.
so
Done. Now, the next topic is the energy of parallel plate capacitor. Right. So we already know that energy is work done, right? And then this is what? This is V dq. Okay. So this is small work done, and if we integrate this, so then we'll get W, so this we have already done. So this is Q by C dq from 0 to Q. So we will get energy which is Q square by 2C. So I'm not deriving because we have already done this part. So energy is Q square by 2C, right?
Yes.
Which is equal to half CV square, which is equal to Q into V. So this part we have already done, right, Aisha?
Yes.
Okay, and please note it down, and then we'll do the energy density.
Also,
Yeah. Okay. Okay, you have to remember these. So make a note of only the formulas and write it, or make a sticky note. So you have to remember these formulas, right? Now the next is energy density of a parallel plate capacitor, right? So energy density means that this is small u. So energy density means that we are calculating energy divided by what? Density means what? Yes, energy density. So what do we mean by density? If I ask you mass density, so what is mass density? Yes, mass density. And remember, this is volumetric. So what is mass density?
M
Yes,
by V.
m by v, right? So density meaning divided by volume. If you are calculating the volumetric density, right? So this is divided by volume. And we already know that this is the plate, right? So this area is what? This area is A, and this distance is what? D. So what would be this volume then? What would be this volume?
So for mass density will be M by D.
Yeah. So I'm asking that what would be this volume? If you have this area and then this distance D between them.
A
So
into D.
A into D, right? Good. So A into D. So this is U by A into D. Okay, and U we already know that is half and Q square, or let me write it as half CV square, right? And this is A into D. Clear? So now we have to, what is capacitance of a parallel plate capacitor? Yes. What is capacitance of a parallel plate capacitor?
By V.
Q by V. But I'm asking in terms of A and D. So A E epsilon naught by D. And then this is V square, and then this is A into D. Right. So this A and A cancels. And what is potential in terms of electric field? Can you tell me? In the case of air, what is the potential? Clear?
Yes.
So this is epsilon naught E square and D square. And then you have this 2 and D and D squares. This one cancels. And now what I can do is that I can multiply this by epsilon naught and divide it by epsilon naught. Okay. So what will I get? Oh, so I have, yeah, so this is, okay, now what should I do? So this is epsilon, right? Now what I can do is that this is epsilon square E square, right? So how, oh, this is done. Why I was, so this is what is called the energy density. Half epsilon naught E square. Okay, is this part clear to you, Aisha?
Yes, sir.
Yeah, please note down this part. So I was trying to write it in terms of sigma, but that is not necessary because epsilon is what? This is sigma by epsilon naught. So E square is sigma square by epsilon naught square. So we can, this part is true, but we can also write this as half epsilon naught and then sigma square by epsilon naught square. So half sigma square by epsilon. This we can also write, but this is correct. Okay, whenever you have noted it down, please tell.
Also.
Done. Okay, so now should we go ahead because only you are here. So should we go ahead or should we stop here? Right, because only you are here. So what should we do? Should we do more things or should we stop at here? What do you think?
Anything is fine, but then if the others join, it will be
Yes?
like they'll be backward.
Yeah. So should we stop at here? What do you say?
I think we should stop because when the others join, they will be having a recap, so it will take time.
ठीक, ठीक. Okay. Okay, so Allah Hafiz, Aisha, and see you in the next class. And you guys, you start revising, right? So the
Yes,
exams, yeah, you start revising, and whenever you face any doubt, so in which chapter do you think which is more difficult for you? Which chapter?
I think the second chapter has a lot of formulas, so it's
Second chapter. So we are still doing the second chapter, right? We again repeated in this NEET class.
yes, sir, because we use a lot of differentiation and integration here. So
Okay, so okay. So what I will do is that yeah, in some portions of second chapter I will write.
Yes.
Okay, and you what you do is that you pick up those topics where you see that it is difficult for you, right? So in that way, I will just do those topics for you. Okay.